Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are going to talk about the topic that is the photoelectric effect. But before starting the topic, I want to tell you one thing, that if you are a student of FSC classes, BSc classes, BS Physics or MSc Physics classes, then this lecture on the topic of photoelectric effect is going to be very helpful for you, and you will learn all the concepts related to the photoelectric effect in this lecture. So let's start our topic with the history of the photoelectric effect. So first of all, in research of the nature of the light is known to be started in ancient Greece, where the philosophers like Plato, Socrates, Aristotle and Pythagoras and some of the other scientists gave their opinion about the matter, and also a very famous Muslim scientist, mathematician, physician, astronomer, and he also known to be the father of the modern optics, and his name was Ibn al-Hasan. He worked a lot on light and vision. Then on 1672, Isaac Newton gave his corpuscular theory, and he says that light is made up of particles. Light has a particle nature. But still some of the scientists like Huygens, Thomas Young and Jean Fresnel and some of the other scientists say that light have the wave nature. And on 1678, Huygens in his theory says that light have the wave nature. Light have the wave nature. And then on 1801, Young's double slit experiment was performed, in which light is showing the interference and diffraction. And these are basically the properties of the wave. So Young's double slit experiment says that light have the wave nature. And then after that on 1865, basically on 1865, the Max Planck gave his explanation about the light, and he says that light is an electromagnetic wave. Basically light is made up of changing electric and magnetic field, and he also says that light is a wave. Light has the wave nature. Then after that on 1887, Heinrich Hertz designed an experimental setup for test the hypothesis given by the Maxwell. To test the hypothesis of the Maxwell, and in this experiment that he designed with the spark gap generator, he observed basically the phenomenon of the photoelectric effect. But at that time he was not interested in photoelectric effect, so he did not create any theory about the photoelectric effect that can explain the phenomenon of the photoelectric effect. Then on 1905, basically on 1905, and that was Heinrich Hertz's experiment. That was the first step toward the explanation of the photoelectric effect, basically. And then on 1905, Einstein explained the phenomena of the photoelectric effect, and it took 10 years for its experimental proof. And on 1916, Silicon oil droplet method was performed, and to check the Einstein hypothesis. So Einstein hypothesis was correct, and then Einstein basically, when the hypothesis of Einstein was proved correct, then Einstein awarded with the Nobel Prize in 1921. In 1921, Einstein awarded with the Nobel Prize due to the explanation of the photoelectric effect. So that was a short history toward the photoelectric effect. So before 90s, it was the debate that light is a wave or a particle. But after that, in 1905, Einstein explained the phenomenon of photoelectric effect and says that light have the dual nature. Sometimes it behaves like a wave and sometimes it behaves like a particle. Mean to say that in Young's double slit experiment, it shows the diffraction and interference, so it behaves like a wave here. And in case of photoelectric effect, it behaves like a particle. We will also saw this in a few minutes later. So And not even the light, the de Broglie hypothesis says that every object, every matter have the dual nature. It has the wave nature as well as the particle nature. The Einstein equation, we know that E is equal to h nu and E is equal to mc square, mass energy conservation equation, and that equation was given by explaining the phenomenon of photoelectric effect. So E is equal to mc square and m into c dot c. And E is equal to P dot C. We can write M into C. Basically, C is the velocity of the light. So mass into velocity gives us the momentum. So momentum dot C, P dot C. E is equal to P dot C. We replace the value of the E by this P dot C. So P dot C becomes equal to H into nu. Nu basically is the frequency of the light and H is the Planck's constant. So P becomes equal to H nu divided by C. We divide the C here and P is equal to H C by nu. H over C divided by nu. And P becomes equal to H divided by lambda. Lambda is the wavelength of that object by which we are finding out the wavelength of that any object. So lambda becomes equal to H divided by P. And lambda becomes equal to H over m into v. We can write the momentum as mass into velocity, and basically here c divided by nu gives us the lambda. Lambda is the wavelength of the object, or if you are finding out the wavelength of any object, then lambda will be the wavelength of that object or that particle, and lambda becomes equal to c divided by nu, or you can write this as lambda becomes equal to c divided by f. F and nu are the basically the frequency of that object. And lambda becomes equal to h divided by m into b. V is the velocity of that object. So we can write here h is the Planck's constant having the value 6.626 cross 10 raised to the power minus 34 joule second. And now we can write this, if h is the Planck's constant and v is the velocity, then we can write this equation. These are the constant values. Then if these are the constant values like h Planck's constant and v, then we can find out a relation between the wavelength and the mass, that is the inverse relation. It shows that the mass of the object is inversely proportional to the wavelength. Mean to say that if the mass will be greater than the wavelength of the object or that particle will be so small. If the mass will be greater than the wavelength will be small, and if the mass will be small, then the wavelength will be greater. Mean to say that if we are finding out the wavelength of an object that has a very low mass like electron mass, then the wavelength will be visible as that of, we are finding out if the wavelength of the ball, like cricket ball, if we want to find out the wavelength of the cricket ball, then place the mass of that cricket ball and its velocity by which it is moving. So we can find out here the wavelength of that cricket ball, and even any object we can find out the wavelength of that object because it has a dual nature according to the de Broglie hypothesis also. So if the mass will be greater than the wavelength will be so small, that's why we cannot observe the wave nature of the bigger object than that of the, you can say, than that of electron, because h Planck's constant value is so small. And if we have an object that have the value of the mass approximately like relative to that of the h Planck's constant value, then the wavelength will be visible. Otherwise this will be so small value and we cannot observe this. This wavelength value will be negligible then if we have the greater value of the mass here, because the wavelength and the mass relation is inverse. Now comes to the topic, our topic, photoelectric effect. So at that point one thing is clear, that light have the dual nature. It sometimes behaves like a wave and it sometimes behaves like a particle. That was the explanation that was given by the Einstein, that I will also explain this. Now the definition of the photoelectric effect. Photoelectric effect, and one thing, that photons are the charge-less particles, mean to say that these have no charge and no mass. Rest mass of the photon is 0 and there is no charge onto the photons. and photons have the speed of move with the speed of light, and their speed of light is equal to 3 cross 10 raised to the power 8 meter per second. And now comes to the definition of the photoelectric effect. When a light of a particular frequency shine on the metal surface, then the electron ejected from that metal surface, mean to say that instantly electron ejected from a metal surface when a light of a particular frequency. The word particular frequency is very important in this topic. If light shine on that metal surface, then the electron absorb that light photon and eject from that metal surface. And this is the setup. This is a light source. This is the electrode having negative charge, and this is the positive charge. These are connected with the voltage battery of voltage V, and basically it is a galvanometer to detect the current, flow of current. When a light shine on that electrode, then it ejects electron from that metal surface, and electron ejected and it moves toward that positive charge plate, and we can find out then these electron moves toward that in this circuit, and we can find out basically the electric current by this galvanometer. Now comes to the classical views of the photoelectric effect. Basically, classical physics try to explain the phenomena of the photoelectric effect, but it fails. Because what was the reasons that the classical physics failed to explain the phenomena of photoelectric effect? These are some of the reasons that one of the big reason of not explaining the phenomena of photoelectric effect by classical theory, that is, it considered the light as a wave, not like a particle. And by considering the light as a wave, this does not make any sense by the frequency. Mean to say that the energy of the light is related to the intensity of the light in classical physics. And classical physics says that light is made up of changing electric and magnetic fields. Mean to say that changing electric and magnetic fields make an electromagnetic wave, and along the y-axis there is the value of changing electric field, and along the x-axis there is the value of the changing magnetic field. Electric field value is equal to E naught sine omega t. E naught basically is the amplitude of the electric field, and omega is the value of the angular frequency, and t is the time, and B naught is the value of the changing magnetic field, amplitude of the magnetic field. And if we have a plane like x, y and z axis, and this is the x axis, z axis, it is the y axis, and it is the z axis, then our light wave is traveling along the z axis, and along y axis there is the value of changing magnetic electric field, and along the x axis the value of the changing magnetic field, and these changing electric and magnetic fields make an electromagnetic waves. And most of the time the information that is delivered from one point to another point in the world by these electromagnetic waves. And intensity of the light wave is directly proportional to the square of the amplitude of the wave. Mean to say that when we increase the intensity of the light, then we are going to increase the amplitude of that electromagnetic wave. And intensity, by increasing the intensity of the light, the kinetic energy of the photoelectron, emitted photoelectron, will also increases according to the classical. When we increase the intensity of the light, then the kinetic energy of the emitted photoelectron will also increases, because when we increase intensity, we are going to increase the energy of the electromagnetic wave, and when a higher energy wave strike within electron on the surface of the metal, then it eject the electron with the greater kinetic energy. Mean to say that the kinetic energy of that ejected photoelectron will increases. And in case of frequency, does not make any sense in classical physics. Change of frequency does not matter. Mean to say that classical says that at any frequency you can perform the phenomena of the photoelectric effect. But the condition is that there will be a time delay. If you are using a light of a very low frequency, then it takes so much time to eject an electron from the metal surface. Mean to say that the energy is transferred in continuous manner onto the metal surface. If you are applying a low frequency light, then this light is to be absorbed by that electron in continuous manner, and it will gain a value of energy that it can break the binding forces and eject from that metal surface, and it takes so much of the time. So that's called to be the time delay. So in 1905, Einstein explained the phenomena of the photoelectric effect. Basically, it was a prediction that was given by the Einstein, and it took 10 years for its experimental proof. And on 1916 or maybe 15, Millikan proved this by finding the experimental value of H Planck's constant, and it was correct with the 0.5% of the experimental error. And in this, Einstein says that light waves consist of small tiny packets of energy, and he gave the name of these small tiny packets of energy as the photon of light. And every single photon had the wave nature. Why? Because when in young double slit experiment was performed, when we throw a single photon between the partition of the slit, then it was showing the phenomena of the interference. When we throw a single photon between the partition of the slits, then it was performing the phenomena of the interference. Then we can say that only single photon also have the wave nature, and this photon of light having energy E is equal to h into nu. H is the Planck's constant and nu is the frequency of that light photon. In photoelectric phenomena, basically, when a light of a particular frequency shine on that metal surface, then this photon of light absorbed by one electron into a single atom, and this electron absorb this light photon and eject from that metal surface. And one thing must be remembered, that only single electron can absorb a single photon and eject from that metal surface. In some of the rare cases, very rare cases, maybe one electron absorbs two photons of light. And when this happens, this is the experimental setup basically. This is a plate having the negative charge connected with the negative terminal of the battery. This is the positive plate connected with the galvanometer, and it connected with the positive plate, and V is the potential of the battery. When a light of a particular frequency shine on that metal surface, then electron ejected from that metal surface. And one thing, these electrons, ejected electrons, will not have the same kinetic energy. Why? These electrons emitting from a same metal with the same light having the different kinetic energies. The reason is that on the surface of the metal there are many electrons are present on that metal surface. We take only some of the atoms, like this atom, let's suppose these 4 atoms, we take only 4 atoms for understanding. So when a light photon strike with that electron, this electron basically is to be free, and require less energy for its ejection from that metal surface. And the electrons under the metal surface, when we are going to deeper to the metal surface, in middle of the metal surface, there are also the atoms are present and electrons are also present. So when light absorbed by this electron absorbs this photon of energy h nu and eject from that metal surface with a greater kinetic energy. And when same light photon is absorbed by this electron maybe, so this electron is bonded with the other atoms, and this electron also face the opposition by the other electrons. When these electrons come to that place and become a free electron and eject from that metal surface, then most of the energy is used to overcome the binding forces, so that the electron that ejected from the surface of the metal will have the greater kinetic energy, and the electron that is ejected from under the metal surface, from the core of the metal surface, from the middle of the metal surface, then this electron will have the lower kinetic energy than that of the electron that ejected from the surface of the metal. So that was the reason that the kinetic energy of the electrons that are emitting from the same metal surface with the same light having the different kinetic energies. And one thing, by increasing the intensity of the light, the number of the photons that are interacting with the electrons onto the surface of the metal are between the atoms that are present between the metal or middle of the metal. Also the photons strike with the electrons that are present in the middle of the metal. So when the photons strike with the electrons that are present on the surface of the metal, then when we increase the intensity of the light, then the number of the photons will increases. When number of the photon increases, then greater number of the photons mean to say that the greater interaction between photon and electron, mean to say that the greater electron will be ejected from that metal surface. By increasing the intensity of the light, the number of the photons increases. And one thing, when we increase the intensity of the light, mean to say that the number of the ejected electron increases and number of photon increases. And when the number of electron increases, it means that the value of the current will increases. But the energy of the photon will remain same. When energy will remain same, it means that the kinetic energy will remain same for the photons. Mean to say that the greater maximum kinetic energy of the photoelectron will remain same and does not change by changing only the intensity of the light. Only the number of ejected electron or photoelectron will increases by increasing the intensity of the light, because the interacting number of photon increases in this way. And in this way, when we say the number of photoelectron increases, it means the value of the current increases, but their kinetic energy does not affected in this way. And what is the intensity basically? Intensity can be defined as power per unit area. Power per unit area is the intensity. Power passing through the unit area in unit time is said to be the intensity of the light. Now, what is the work function basically? What is the work function? Work function can be defined as the minimum amount of energy required to eject electron from the metal surface is said to be the work function. Mean, if we have an atom, let's suppose this is an atom, for understanding, when a light photon strike with that electron and this electron absorb this light photon and eject from that metal surface, so there will be a binding force between the nucleus and the electron. To overcome this binding force, the energy of the photon is used for this purpose, and that is called to be the work function of any of the metal, and it depends on the material of the elements. Like in alkali metals, when we go from up to down in groups, the ionization energy decreases. So in alkali metal of the first group, sixth period, these are like lithium, sodium, potassium, rubidium and cesium. So in case of cesium, forget the sunlight, it can also perform the photoelectric phenomena even at the candlelight maybe. So mean to say that at very low frequency the cesium can perform the phenomena of the photoelectric effect. Why? Because there are the distance between the nucleus and the valence shell electron is greater, mean to say that there will be require a less energy to release this electron from that metal. So for the cesium, the work function is very low. Now comes to the equation of the work function will be E is equal to h nu. That is the equation of the Einstein, that was given by the Einstein. And we can also say that the work function will be equal to h into mu naught. Mu naught is the threshold frequency. What is the threshold frequency? Basically, threshold frequency can be defined as the value of the minimum frequency at which the phenomena of the photoelectric effect can be performed. That's called to be the threshold frequency. So work function is basically is the we can find out the work function by multiplying h Planck's constant with the value of threshold frequency, and we can find out also the threshold frequency as threshold frequency will be equal to 5 over h Planck's constant. So frequency can be defined as the minimum amount of energy required to eject an electron from the metal surface. So when we increase basically the frequency of the light, then it means that we are going to increase the energy of the light photons, because energy depends on the frequency of the light. Energy depends on the frequency of the light, and it is independent of the intensity of the light. By increasing the intensity of the light, only number of ejected electron increases, but their kinetic energy remains same. Maximum kinetic energy will remain same. But when we increase the frequency of the light, then it means that we are going to increase the energy of that light photon. And when a greater amount of energy have the light photon strike with that electron, then this electron will also use some of the energy in doing work function, and the remaining will be used into the increasing the kinetic energy of the electron. And in this way we can find out, we can also write an equation that was given by the Einstein, that the kinetic energy maximum of the photoelectron will be equal to energy of the photon minus the work function, and energy of the photon is that we are placing h nu minus phi is the work function. So kinetic energy maximum will be this, and kinetic energy may be approximately equal to kinetic energy maximum approximately equal to 1 by 2 mv square. So we can say that 1 over 2 mv square is equal to h nu minus 5. And we place the value of the work function value, that's equal to h into mu naught here, h into mu naught, h giving common, taking common, and nu minus nu naught is the value of the kinetic energy. That's the equation that was given by the Einstein for the explanation of the photoelectric effect basically. Now, our frequency of the incident light will be greater than that of the value of the threshold frequency. The value of the nu always must be greater than that of the threshold value. In this way, we can only perform the phenomena of the photoelectric effect. If the frequency of the incident light photon is less than that of the threshold value, then we cannot be able to perform the phenomena of the photoelectric effect. Either we are going to increase much of the intensity, but the energy of the single photon will remain same. If this single photon of light have the energy h nu, then by increasing the intensity of the light, it means that we are going to increase the number of the photon only. But still, the energy is concerned with the frequency of the light, or you can say that it concerned with the c divided by lambda. It concerned with the wavelength of the light. By the light having the longer wavelength, its energy will be low, and light having the shorter wavelength, its energy will be high. So by lowering the wavelength or by increasing the frequency, we are going to increase the energy of the incident light. So when we only increase the intensity of the light, then the number of the photon increases. No doubt increases number of the photon, but their energy will remain same. And when their energy will remain same, then we can say that if the lower energy, the value of the frequency is lesser than that of the threshold value, the incident light photon having the frequency less than that of the threshold value, then by increasing the intensity, the energy of the light photon will remain same, and we will not be able to perform the phenomena of the photoelectric effect by only increasing the intensity. And one thing must remember, that on the threshold value, we need to say that if our incident photon have the greater frequency than that of the threshold value, at that point when we increase the intensity of the light, then it means that when increase the intensity, the number of the photons that we are inserting on that metal surface, greater number of the photon, intensity increase means greater number of the photon, and greater number of the photon will interact with the greater number of the electron, and greater number of the electron will emitted from that metal surface, and greater number of the electron makes the greater amount of current. You can say that the value of the current will increases by increasing the intensity of the light at this condition, when our frequency is greater than that of the threshold value. And if this condition is not fulfilled, either we are increasing so much intensity of the light, the photoelectric phenomena will not perform. So now comes to the threshold wavelength, or you can say that the cut-off wavelength, and this also, the frequency can also be said that the cut-off frequency or the threshold frequency. So in threshold wavelength, we also know that our work function is equal to phi is equal to h into mu naught. Mu naught is the threshold frequency, and we can say that phi is equal to h into c divided by lambda naught. Lambda naught basically the value of the threshold wavelength, the maximum wavelength basically. The maximum wavelength at which the phenomena of the photoelectric effect can be performed, that's called to be the threshold wavelength, or you can say that the cut off the wavelength. And we can find out its value as lambda naught is equal to hc divided by 5. hc divided by 5. That is the value of the wavelength. I mean to say that the maximum wavelength at which the phenomenon of the photoelectric effect can be performed having this value. Lambda naught is equal to hc divided by 5. 5 is the work function of the metal. So now that was the explanation that was given by the Einstein, and in equation of this equation, what this equation basically tells us, the kinetic energy of the emitted photoelectrons, is equal to h nu, the energy that was given by the light, photons, the total amount of energy, minus work function, the energy that used to break the binding forces between the nucleus and the electron, or you can say that the energy that required to eject the number of electron from the metal surface. That is said to be the work function. So minus work function, that will, the remaining energy will be used to speed up these electrons. So you can say that the kinetic energy, the remaining energy will be the kinetic energy of the electrons. So now that was the explanation that was given by the Einstein to explain the phenomenon of the photoelectric effect. So now we will find out the stopping potential of the photoelectrons, the electrons that are emitting when a light of particular frequency falls on that metal surface. So this is the experimental setup that used by the Philip Lenard for checking the kinetic energy of that photoelectrons basically. So it consists of an evacuated glass tube, and this, why we are using the evacuated glass tube here, because we don't want from the photoelectron to interact with the gas atoms, any kind of gas atoms or molecules. So in this way it consists of an anode and also a cathode. This have the negative charge, this have the positive charge. And one thing that this collector, you can say collector, charge on that plate can be controlled by this variable resistor. I mean to say that the potential difference can be changed by this variable resistor. If we move this terminal toward the negative terminal, it becomes negative, and if we move this point toward the positive terminal, then it becomes positive. Current will flow from that point to these batteries and also make a circuit. So when we are performing our experiment, first of all we place this terminal at that point. Let's suppose at that point. In this way this become positive, because there is no potential difference between these two terminals. When light shine on that metal surface, electrons eject from that metal surface, and every electron, photoelectron, that I have told you previously, every photoelectron have the different kinetic energies, will emit with the different kinetic energies, and some of them have the greater kinetic energies and some of them have the smaller kinetic energies. So the electrons with the smaller kinetic energies, with the low kinetic energies, will bounce back when we place this terminal, let's suppose at that point. The potential difference, so potential difference will create it between these two plates and it will become negative. So let's suppose that the photoelectrons with the smaller kinetic energies reach at that point, and then due to this negative plate these electrons bounce back, and some of them, like one or two electrons, still reaching at that plate and performing the current and giving us the current by the ammeter. And we have also here the voltmeter for finding out the potential difference basically. So some of them, most of the electrons bounce back. The photoelectrons which have the lower value of kinetic energy is bounced back by this potential, at this potential, and the photons, the photoelectrons that have the greater kinetic energies are approaching still at that plate. So now we want that no one electron will reach at that cathode. So we more negative this plate and place this terminal at that point. So now this plate will become more negative, and the electron that are approaching to one or two electron maximum kinetic energy electron that are approaching to that plate now bounce back from that point, and we will find out that potential at which all the photoelectrons, even with the maximum kinetic energy electrons, bounce back. We find out here the potential that's called to be the stopping potential. So now we find out the kinetic energy here. Kinetic energy will be equal to, maximum kinetic energy will be equal to charge into potential difference, and charge basically are the electrons. So we place here E into V naught. We find out here from that point the V value of the V naught, and we also know the equation given by the Einstein for the photoelectric effect, and that is equal to h nu minus h nu naught. That's the work function, that's the energy of the light photons, and that is the kinetic energy maximum. And we eliminate here h Planck's constant nu minus nu naught, at taking common, and also we place here the value of the kinetic energy, and it is at E into V naught, and V naught will be equal to h nu minus nu naught over E. By using this equation, Millikan find out the value of the h Planck's constant and proves that the explanation that was given by the Einstein to explain the photoelectric phenomena is correct. So now comes to that point. Classical physics says that frequency not concerned with the photoelectric phenomena, means to say that frequency does not matter in photoelectric effect. It does not place any difference onto the photoelectric phenomena. So the experiment shows that at a particular frequency the phenomena of the photoelectric effect can be performed. Let's suppose we have two light waves of two different frequencies. One of them is having the lower frequency, and the other light have the greater frequency. Let's suppose that we have a blue light, then it gives us and on y-axis there is a photoelectric current, and this is the negative value of the potential, and here is the positive value of the potential. So we saw that a frequency f1 frequency, light of f1 frequency, making a graph, and when we negative this terminal, we don't want from the electron to interact with that plate. When we move this terminal toward negative point, we move this at that point, then some of the electron stops. When we move this terminal toward negative, some of the more electrons will stop. And when we move at that point, let's suppose, then all the electrons approaching to that plate will cease, and make a graph. It makes a graph like this. At that point, the photoelectric current is zero, mean to say that all the electrons will stop reaching toward that plate. Now, if we have a light with a greater frequency, a higher frequency than that of f1, mean to say that when we change the frequency of the light, then we are going to increase basically the energy of that light. And when the light photons interact with the electrons onto the metal surface with the greater energy, then the photoelectrons, emitting photoelectrons will also have the greater kinetic energy. And kinetic energy greater means with the great velocity. To bounce back these number of the electrons, we have to apply here the more negative potential. So we also have to move this terminal toward that negative terminal. So they require a more negative potential to stop these photoelectrons. So let's suppose they will be stopped at that point. So there are the two values of the stopping potential here. This is the value of the stopping potential, and also this is the value of the stopping potential. If the frequency is low, like f1 value, then this is the value of the stopping potential. We require a less stopping potential, a low stopping potential to stop these electrons. And if we apply a light of a higher frequency than that of f1, then this will be the value of the stopping potential. Mean to say that the greater value of the stopping potential we require here. And the value of the photoelectric current will remain same in both of the cases. Photoelectric current will not be affected by increasing or by decreasing the frequency of the light, of the incident light. So now comes to the intensity, case of intensity, change of intensity of the light. When we change the intensity of the light, let's suppose we have, and f2 is greater than f1. Now in intensity case, we have two lights having the frequency, same frequency, and we only change the intensity of the light in this case. So one light, let's suppose making the graph like this, and our required stopping potential to stop these electrons, that these electrons not approach to that negative plate. These electrons stop maybe like this at that point, and this is the value of the stopping potential, let's suppose, for intensity I1. Now, if we increase the value of the intensity, if we increase the intensity, then it means that the energy remains same. The photons that are interacting with that metal surface will remain same. Their energy will remain same, but only the number of the photon will increases. Number of the photoelectrons, will be increases. So when the number of the photoelectron increases, it means that the value of the photoelectric current increases here. Value of the photoelectric current increases, and we apply the same negative potential here to stop these electrons, because their kinetic energy does not change. By increasing the intensity, their kinetic energy will remain same, but only their number will change, mean to say that their counting will increases. Greater number of photoelectron increases by increasing the intensity of the light. So now at that point the stopping potential will remain same. Only the value of the photoelectric current will increases. Now come to the change of the kinetic energy and frequency. We have a graph here. This is the value, positive value of the kinetic energy, and this is the negative value of the kinetic energy basically. So for the different metals, the value, threshold value of frequency will be different. Minimum value of the frequency will be different for the different metals. So we are let's suppose we have two metals. For one metal we have the value of the threshold frequency like this. At that point, the mean to say that at that point electron will start ejecting from metal surface, and when photoelectron eject from the metal surface, it means that they have some kinetic energy, and its value will be like this for one metal. For metal number 1, let's suppose we have another metal and it has the value of the work function is greater. So in that case, the value of we require threshold frequency will be at that point, threshold value of frequency will be greater, and it makes a graph like this: metal 2 for the second metal and for the first metal. And also, if we draw this graph like toward this, it also has the negative values of kinetic energy, but kinetic energy will not be negative at this. So we can say that this is the graphical representation for the kinetic energy and frequency. So that was basically the photoelectric effect. Hopefully you will like this video, and if you think that by watching this video you have learned something, so please share this video, like this video, and